Swayam Prabha. Digital India. Educated India.
So, friends, we are talking about line balancing, and we said that it is very important for flow lines for mass production system. Then we said there are two types of lines, one is called fabrication line, another is called assembly line, and the various algorithms which are having, they belongs to assembly line balancing. And for fabrication line, it is more engineering aspects which can be applied to balance the lines. So, in assembly line balancing, we said that several techniques are there, and in the previous class we talked about ranked positional weight technique. And in today we are talking about few more techniques of line balancing. We are starting with the technique which is called largest candidate rule. The largest candidate rule, as I said earlier also, in this we arrange the various tasks, we assign the various tasks based on the element task time. Based on the task time, we assign the task to the different workstation. The procedure is same. The first step, this is the activity time and predecessor relationship is given to us. Based on this, we will develop the precedence diagram as we did for the ranked positional weight. I have selected the same example as we were doing for ranked positional weight technique, manufacturing of assembly of 300 computers in 480 minutes. And so, we are having a cycle time of 1.4 minutes, that is 84 seconds, and minimum number of workstations required is and minimum required is 7 minimum workstations are required. And in RPW technique, we were able to do that with the help of 8 number of workstations. Let us see here. We are not solving the complete, I will just give you the steps which are different from RPW. So, first step is we should have the information about the various tasks which are required to be done and their immediate precedence, and then we will develop the precedence diagram based on that, and then we will find out, we will arrange this table in the descending order of task time. The element which is having the task which is having the highest task time is put at the top. Element task H has the highest time, so it is put at the top. Then we are having 55 put number 2, then we are having C time 50 is placed here, then we are at G 45 put here, then 45 arranged here, 42 arranged here, then there is another 42 that is arranged here. So, in this manner we have arranged this information about task and task time in the descending order of their task time, and this is the precedence of these elements. So, now we will again do the same kind of exercise. We will open the workstation number 1 and see that how much time is available with this. Workstation number 1, 84 seconds are available with us, and then we will see that which can be assigned. So, we will identify the elements which are having no predecessor. So, it is element A, F and E. Out of that, which is having the highest priority, A is having the highest priority, and time of A is 55, which is lesser than this. So, I will assign A, and I say that now 55 is assigned. So, 29 is available. Once A is assigned, A is deleted from this list wherever A is appearing. So, I will go for the next iteration, and now which are the elements not having any predecessor? We are having element C, we are having element D, we are having element B, and we are having element F and E. Out of that, the highest priority is for C, highest priority is for C, and the time of C is 50 seconds, and which is more than time available 29 seconds. So, we cannot do that. Now, let us see which one is the next T D. How much is the time required for D? 42, which is also greater than 29. So, D can also be assigned. Then there is element B, which is having a 30. Then there is a B, which is having a time of 30. This is also greater than 29. So, B also cannot be assigned. Then we are coming to F. Next is F. So, I will see F. F is having 25, which is lesser than 29. So, I will assign F here and 29, F is 25. So, 4 is left here. So, like this. So, workstation number 1 is clear. Then I will open the workstation number 2. Once F is assigned, I will delete F from this particular table. So, the procedure is same as we did for RPW technique, and in this way we can find out the efficiency, but you will find this method is less efficient as compared to the RPW technique. Now, let us see one more method, that is Kilbridge and Webster method. Same procedure, we are having task time and precedence relationship, and we have to balance it for 84 seconds. And so, here in this case we will count the number of followers. We can just for the sake of convenience, we will start from this end. N is not having any follower, so its value is 0. M is having 1 follower, so its value is 1. L is having 1 follower in the form of N 1. Then we are having K has 1 follower, so its value is 1. Now, let us see J. How many followers J is having? J is having 1, 2 and 3. 3 tasks are following J. After doing J, I have to perform 3 more tasks. So, total number of followers for J is 3. Similarly, I can say for I it is 1 only. So, done. Now, let us see for H, it is interesting to see for H. Which are the tasks which are following H? H is being followed by task J, H is being followed by J, I, L, M, K and N. So, there are 1, 2, 3, 4, 5, 6. 6 tasks are following task H like this. And if I say B 7, 6 plus 1 7, H is also counted here for B, H and all these things. So, 7. So, like this I can count for A, how many tasks are following A? Except these 2 tasks, all other are following A. So, total tasks are 14, out of that eliminate this minus 3 itself and 2 more 3. So, 11 tasks are following A. So, like this we can calculate the number of followers for each task and then arrange this table in the descending order of followers. Task which is having the highest follower is kept at the top and the element which is having no follower is kept at the bottom. And then we can do the assignment same as we did for RPW technique as well as we did for largest element rule also. So, in the same manner we can open the workstations one by one. Workstation number 1, 84 seconds are available. The tasks which are available are which is not having any predecessor A, E and F. This is more matching with the you will find RPW technique, and out of that the highest priority is for A and the time for A is 55. So, we will assign A and then we will have minus 84 minus 55 is 29. So, 29 is available. Now, once A is done, we are having priority for we are having E, F, B, C and D. B, C and D. Out of that the highest priority is for E. Highest priority is for E as well as F. When there is a tie, find out the element which is having the higher time. So, E and F both are having no predecessor. Out of that and both have the same priority, out of that we will select F First we will select F, because F is 25 and see that we are available just so 4. So, now no more element. So, open the workstation number 2 and keep on doing that as we did for RPW technique or largest element time technique, and we can assign all the tasks to the various workstations, and again we can calculate the line efficiency. So, these are the 3 methods which we have studied, which are almost similar to each other, only criteria is different. In one case we are talking about the number of followers, in second case we are talking about the task time. In the RPW technique we are combining the 2 aspects based on the number of followers, their timing as well as the timing of the element. Together we have calculated the RPW, and based on that we have assigned the various tasks to the different workstations based on the priority taken on the RPW basis. Now, let us see one more example, example of Moody and Young 2-phase method. I have taken a different example just to break the monotony, and now we are having an example which is having how many workstations we are having? 1, 2, 3, 4, 5, 6, 7, 8, 9. So, total 9 tasks are there, or I can count here also 1, 2, 3, 4, 5, 6, 7, 8, 9. So, 9 tasks I am having here. Let me erase this. 9 tasks I am having. Okay. And total time of this task, if I have T A plus T B plus T C up to T I is equal to 37. So, total T is equal to 37. 5 plus 3 8 plus 4 12 plus 5 17, and there is something is hidden here for E. E is 1, I believe. E is 1, we will get to know, and then based on that I get a total time of 37. So, total 37 units of time is required to do the complete assembly. So, the first step, the first phase is, the first phase of this methodology is prepare the P matrix and the F matrix for all the tasks which are need to be carried out. P matrix is the predecessors and F matrix is followers. P stands for predecessor and F stands for followers. Task A is not having any predecessor, but it has 2 elements which are following, that is B and C. So, I will write B and C also. So, there is no 0 is that means there is no predecessor, but 2 followers. Task B is having 1 predecessor and 1 follower. A is the predecessor and D is the follower. So, task B is having A as a predecessor and D as a follower. Task C has A as a predecessor and D as a follower. Let us see task D. Interesting. Task D is having 2 predecessor in the form of B and C. In the form of B and C, we are having 2 predecessors and it has 3 followers, E, F and G. So, E, F and G are 3 followers for D, and in the same manner we will see for E. E has D as a predecessor and I as a follower, and so on. C as element I. I is having 3 predecessors, E, H and G. E, H and G, and it has no follower. Then you will find that maximum number of predecessors are 3. So, we have taken 3 columns here. How many columns to be taken? Once we find out the maximum number of predecessors, and rest are covered with the help of zeros. Similarly, in the follower matrix we are having maximum 3 followers, rest are covered with the zeros everywhere. So, this is how we can prepare the P matrix and the F matrix. Now, let us see how to do further. So, I have reproduced the same matrix which was there on our previous slide here, and now let us follow the steps of phase 1. This we are talking about phase 1, it is a 2-phase method. So, in phase 1, step 1, start with P matrix, select task with all the zeros, that is no predecessor, In this case there is a task A which is not having any predecessor. Go to F matrix and note the task B and C. So, we will locate the task A as the first task. We find it has no predecessor. So, we will locate it here and then we will go further. Now, go to the F matrix and note the task B and C and come back to get back to P matrix, replace element B and C with 0. So, this is going to be replaced with 0, this is also going to be replaced with 0. Now, how many elements we are having which is not having predecessor now? A is already assigned. So, now we are having B and C which is not having any predecessor. So, I will put B and then I will put C also, just like here we are having. Okay. So, B and C have all zeros. So, B and C have been placed in this. Now, we are repeating the step 2, 3 and 4, 2, 3 and 1. Go to F matrix, find out the tasks which are following B and C, that is D. So, come to the D matrix and eliminate this. Okay. So, that will give to us D here. Once we have assigned D, E and F. So, go to E and F and delete this and like this. So, we will get this sequence as a. So, all the tasks has been arranged in the sequence. All the task has been arranged in the sequence as a phase 1 exercise. In the phase 1, by following these 5 steps, we are able to develop a sequence of these tasks based on the their precedence and the followers. Okay. Here you will find that this is slightly inferior to the previous method of RPW and other, because we are only looking at predecessor, we are not taking care of their element times or their number of followers. We are not considering that. Anyway, it has its own strength. So, in the phase 1 we are able to develop this particular sequence. Now, let us go to the phase 2. So, step 5 I have written here till all zeros and the following sequence is achieved. We achieved this sequence. Now, step 6 of phase 1, sorry, phase 1 is continuing. In step 6, we divide the task into workstations with cycle time of 15. In this case, we have chosen this example for a to be balanced for a cycle time of 14. We have to balance this for a cycle time of 14 time unit. So, we will see that we will write the timing element. Task A has a 5 unit, C has 4 unit, B has 3 unit. So, altogether is 12. I cannot add one more D, because that will then violate this 14 time unit of constraint. So, one workstation is having element A, C and B. Then there is second workstation which has element D, G and F, and then there is a workstation 3 which is having H, E and I. So, I am able to allocate all the tasks among 3 workstations, workstation 1, workstation 2 and workstation 3. And workstation 1 S1 is having a time of 12, S2 is having time of 14 and S3 is having a time of 11. Now, I can calculate the efficiency in the same manner as we did for earlier. Total time is 37 time units and divided by number of workstation 3 and they are balanced for 14 divided by 42, and our line efficiency is 88.1%. So, in the same manner I can calculate the efficiency of this line as we did for RPW technique and other techniques. We can in the same manner we can calculate the efficiency of this line. So, it is 88.1%. I want to explain and balance delay is 1 minus efficiency, that is 100 minus 88.1, 11.9 is the balance delay. So, there is a loss of time to the tune of 11.9% is the ideal time in this balancing of the line. Here I am exposing to another performance measure which is called smoothness index. Smoothness index, how smooth is this line? That means whether all the workstation have same time or there is a difference between them, and this is a it is calculated as summation of the difference between maximum time and the station time. Like S max in our case is, if we take say 14 is the X max and we have said S1 is equal to 12, S2 is equal to 14 and S3 is equal to 11. So, smoothness index is 14 minus 12, S max minus S1 whole square, X max minus S2 whole square, S max minus S3 whole square. So, this will be 2 square is 4, 0 square is 0 plus 3, 14 minus 11 is 3, 9. So, 9 plus 13 under the root. So, the smoothness index of this is root 13. Okay. Now, we are going to the phase 2. Now, we are going to the phase 2 with this particular calculations of efficiency and performance. What we do in phase 2 is, we will try to shift the elements from the least to the highest. Can I shift one interchange between the two elements, so that this become better? Like in this case, we can see that if I interchange obviously without violating the precedence relationship, if can I interchange one of the element 5 and 4, D and H, can I interchange D and H or G and H? For that, I have to refer my precedence diagram, whether H is which are the elements which need to be carried out before H. If we look here, H need to be carried out only, E is not a predecessor for H. From this diagram, you will find that E is not a predecessor for H. H can do once F is carried out or D is carried out. So, I can easily replace the elements or G is also done independently. We can do that change transformation, and with the help of that, if I am able to transfer one interchange, so that this is having 13, this is having 12. So, my S max will be, if somehow I am able to shift the timing, and that means elements interchange. So, that this is having 13, this is having 12. So, my S max will be 13 time unit, and then I can calculate the smoothness index in this manner: 13 minus 12 whole square, 13 minus 13 whole square, 13 minus 12, that is under root 2, and my so smoothness index in the previous case it was under root 13, which has been reduced to under root 2. So, that is one advantage I can get, but but my line efficiency will remain same, because I am using 3 workstations with the cycle time of 14. Now, I can apply the second trick here, where we said that we can improve the efficiency by keeping C same and reducing the N, by keeping N same and reducing the C, or in now we can apply this. We can reduce the C from 14 to 13. If I reduce the C from 14 to 13 and with the same 3 workstations and with this smoothness, you will find that my line efficiency increased to 94.9%, which was earlier it was of the order of 88.1. So, with the cycle time of 14, my efficiency was 88.1%, which has been improved to 94.1, and smoothness is also much better. Rather than root 13, it has improved to root 2. So, this is how we can use the Moody and Young method, 2-phase method, by interchanging, refining the solution by exchanging a task between max and minimum Sk to improve the smoothness index. So, we can interchange one element between workstation 2 and workstation 3. So, that my smoothness index is increased and my S max is also reduced, and by reducing X max I can change the cycle time also, I can reduce the I can lower down the cycle time also, that helps in improving the efficiency, line efficiency of the assembly. So, this is the Moody and Young method, 2-phase method, very interesting method, and it gives you an idea about improving the smoothness also. Okay. Now, let us talk about the one more technique, COMSOL, that is a computer method of sequencing operations on assembly line. This is a simulation approach, where in a random manner we are preparing the sequence of the task in a random manner, and then we dividing this sequence into compartments as we did in Moody and Young method, and then we choose the one which require the minimum number of compartments. Compartment means workstations. So, very simple algorithm, and but it cannot be done manually. It is done only with the help of high speed computing power, because if you are having there may be large number of permutation combinations are possible, even if you are having 50 elements, though, which is very small. As I said, in a car assembly and other, this may be in few thousand elements, and then you are sequencing them in random manner, and by that you are creating large number of sequences of this, let us say, for that, and then we are doing the compartment. But with the help of computer, it is very easy. If we are having high speed computing, it can be done very fast. So, procedure wise, let us take the same example as we did for Moody and Young. We construct the list A, element which is having no predecessor, and construct B, list B of tasks have 0 number of immediate predecessors A, and then eliminate the selected task from the precedent and update the list A. Okay? And then update the list B by adding more tasks which have no immediate predecessors. So, we prepare the list B, that is B and C. So, B and C, now once A is assigned, B and C is the element which are not having. So, we will assign B and C, and then we select any one task at random out of B and C. Let us say B is selected, and we will continue this till all the tasks are assigned, and in this manner we will get a sequence of the task, starting with A, then we will get B, and then we will get C, and like this we will keep on doing that, and assigning the task here. And because of this randomness, out of B and C we have selected in random. So, next time it may be possible that C is selected, and that gives you the new sequence to you. So, in that way large number of sequences are created with the help of a computer program, which keep on selecting the tasks which are having no predecessor, and if there is more than one, it select at random, and because of that randomness we get large number of such sequences. So, repeating the steps, select any one task, continue till all the tasks are assigned. We get sequence of tasks, divide them into workstation, find out the number of workstations, and compare the numbers of workstation with the previously retained sequence. If the number of workstation of this sequence is lesser than the previously retained, we retain this one and delete the previous one. But if this is having more number of workstation, then we will keep on retaining the previous one, and in this manner we continue till we are able to get a sequence which require less number of workstations. So, that is a very simple method. Algorithm is very simple, but it require a computational time. If the number of tasks are more, a high computational time is required, but it is a very good efficient method, because it almost explore each and every sequence, each and every alternative assembly line, and that way it is very efficient, very effective method. I should not say efficient, because it requires a lot of computational time. As the number of tasks increases, the computational time also increases. So, friends, up to this we studied the various techniques, started with RPW technique, then largest element method, then we talk about Kilbridge and Webster method, then Moody and Young method, and the COMSOL method. Now, let us talk about some of the concepts. What can be the possible? This is a very simple situation we have taken. There may be a situation where certain fixed machine is there, or some facility is there, and that machine or facility is at a particular station. That means, that particular task can be carried out, let us say workstation at in a conveyor. There is one equipment which is available, which cannot be moved to any other workstation. So, there is a equipment which is available here, which cannot be. So, the task which is required to be done with the help of this equipment, that has to be carried out only at workstation number 3. So, that can be a constraint here. So, you cannot do anything, even if you want to shift it to 2 or 4, it is a constraint. In any case, you have to assign the task here. What we can do is, the task, let us say task D which is required to be done here. So, what we do, we will eliminate the task D from the list, we assign it here and we reduce the cycle time of workstation 3 by the task by T D. So, that now this has remaining time, we can assign more tasks to it, but we have to assign in any case task D to workstation number 3. So, this is how we can handle it, though it is very easy, but there may be constraints of that. Similarly, there may be conveyor which is having workstations on both the sides. Work is carried out on both sides of the conveyor, especially assembly of a motorcycle, assembly of a car, such big unit, workers are working on both sides of the conveyor. So, in that case what we can do is, we can divide the total assembly task into two categories, one which is to be carried out by one side, left hand side, another to be carried out by the right hand side, and based then we can balance the two lines independently, and because tasks which are to be conducted on the left hand side to be kept on one side, on the right hand side to be kept on one side. So, this can be easily taken care of by drawing the two precedence diagrams and work independently for optimization. So, we can do that. So, these are the two constraints which I have listed just to further elaborate on this. There may be many more such kind of a situation can arise, or there may be a case where assembly is carried out at different floors. Certain parts are carried out at one floor, another parts are carried out at another floor, depending upon the input components required or sub assemblies required to do the assembly. So, we can very easily bring incorporate those constraints into our line balancing system. There are certain limitations which we keep in mind. Since the activities are manual, so element time may vary from cycle to cycle. Like we said that T A is, let us say we talk about T A is 55 seconds in our RPW technique. It is not possible that in every cycle the worker is taking 55 seconds to perform the task A. Sometime he may take 54 seconds, sometime he may take 53 seconds, sometime he take 56 seconds or 57 seconds, but this 55 second is average of time study. But there may be a time study of 20 such cycles, and we found that average comes out to be 55 seconds, but in actual it may be varying. So, how to handle that? If it requires 58 seconds and you have not having any cushion available with the worker, that means task will not be performed. Task will not be performed and incomplete task will be moved forward to the next workstation, and that we do not want in any circumstances. So, if we find that there is too much of variation in the task time, so we can consider the stochastic nature of the time elements, and we can deliberately imbalance the line. While doing the balancing, we can deliberately imbalance the line. We can keep some cushion, though we are planning for 84 seconds of each workstation. Rather than giving a work content of 84 seconds, we may give a work content of 80 seconds only to take care of variability in the cycle time of that element. Because if we give the cycle time of 84 seconds and it time may vary 86 seconds, 82 seconds or like that, then incomplete task may move to the next workstation. So, in that case we deliberately imbalance the line. There is a research paper in which it says that we follow the bowl phenomena. That means, we can give 83 seconds of workload to the workstation here. Let me draw it again, and we can this is workstation time and this is workstation number 1. So, in the beginning the workstation number 1 can be given 84, because then workstation number 2 maybe we have to give lesser time, and this may be given time of 80 seconds, and then again, because this is all the variability of the previous is going to affect this particular workstation also. So, in that manner we can deliberately imbalance the line, rather than giving the same amount of work content to all the workstation, to the middle one we can give slightly lesser work content to take care of the variability in the cycle times. Second important thing which we have to keep in mind is algebraic sum. We are saying that S k is equal to T A plus T B, but in actual it may not be true, that it may be more, it may be less. If it is a rhythm between the two, this may be same, but if there is no rhythm, there is a discontinuity between task A and B, that Sk may be slightly more than T A plus T B. So, may not be possible that the station time is equivalent to the may not be equal to the sum of the task time, because the work is done in the sequence and there may not be a rhythm between the tasks which are assigned to a particular workstation. So, though I have said here that if the elemental times are varying, we can have probabilistic line balancing, certain algorithm and certain approaches are there for that, we are not considering that here. We can incorporate the variability in the balancing method itself, and we can consider the probabilistic times instead of the deterministic time. We can say that T A is the mean of activity, mean time of is A is 5 seconds, with the standard deviation of T A is 5 seconds, so 2 seconds or 1 second, and we can bring that into the at the balancing stage itself, we can bring that, or we can do pacing with the margin. We are not keeping the rigid line, the workstation, it is not a hard conveyor which is moving. Once you done your task, then you move it to the next, and once it is done, it is moved to the next, and there may be some cushion available, space available, by which if required this task can wait here and this task can wait here. If this fellow is not free, the task may wait here, and if he is able to do it fast, another task is waiting, he can take it. So, rather than having a hard conveyor, we can have a soft conveyor with the help of rollers rather than a belt conveyor. So, that is also possible, and we can decouple it, we can keep a inventory in between the station. So, they are not dependent on each other, and we can decouple the various workstation with the help of inventory, or there may be overlap also, that is also followed, that this worker, though this is workstations are there. So, this worker can start his task from this point and go up to this. This is a normal way, 84 seconds is available during this, but if he is not able to complete, he can little bit overstep and go up to this also. And similarly, he can start bit early also if his task is completed. So, that is called overlapping. So, this worker can also come up to this place and so on. So, based on this, that is the overlap concept we can take use to balance the to take care of the probabilistic timing of the elements. So, this is the concept which I earlier explained. Multi-model, we are producing few units of model A, then we change over and we do the units of B. If the time requirement of at different workstations are different, then obviously dynamic balancing is required. Static balancing is not going to work, and if it is a mixed model, then it is even more severe. Every item is changing and you have to keep on changing, or maybe you have to plan in such a manner that there is minimum ideal time when there is a change from one model to another. So, these aspects also special cases of line balancing, where multi-model or mixed models are there. Now, let us see some human aspects related to line balancing. As I said, in flow shops and assembly line, the absenteeism is highest, because there is a monotony of job, boring, the same kind of task in a car manufacturing. If let us say cycle time is 2 minutes, that means in a shift of 8 hours, 8 hours we can reduce half an hour for lunch, etc., 7.5 hours into 60. So, 450 minutes, and if we are producing a car after every 2 minutes with a cycle. So, 225 times in a day he is performing the same task, and that give him a boredom and monotony. And so, that we have to do something, I will talk about this here. What we can do to break the monotony, we can enlarge the task, rather than he is doing a task of 2 minutes only, we can enlarge, so that he is having a substantial amount of work available with him. That we can do with the help of modular assembly or something like that. We can do the job enlargement, so that he is not confined to a very small task, we give him slightly bigger amount of task. Another way is job enrichment. Job enrichment means along with doing the physical task of assembly, we are engaging him in some creative activities also. Maybe we are having some quality circles or empowering the employees with the help of quality circles and such kind of approaches. So, that he is not feeling bored, he is having something where he can apply his gray cells also, not only the limbs, he is thinking also, he is involving in improving the workstation also, or he can be part of the Kaizen team, quality circle team also, by which he will feel that yes, he is also contributing, he is not only doing the physical activity, rather he is also applying his intelligence and brain also to improve the situation. Another is job rotation also we can apply. The persons who are working on assembly line can be transferred to fabrication areas, from fabrication to assembly area. In the assembly area also you can shift it from workstation 5 to workstation 2, workstation 5 to workstation 11. So, that his monotony is broken, but for this you have to give him training also, you have to develop the multi skilled workers. You have to train him in different for different workstations or different areas. In Japan, this culture is very highly implemented. They rather in their annual appraisal, one of the important criteria for annual appraisal is how many more skills you have learned in the last 1 year. More the number of skills earned in the previous year, that will decide your increase in your salary. So, by that there are two advantages of multi-skilling. One is the monotony is broken. Now, the person is able to performing different type of task on different days. So, or maybe roster is there of a weekly basis or a monthly basis. So, monotony is broken, number one. Number two, if there is a decrease or increase in the demand and you want to rebalance the line, so with the help of multi-skilling that is possible. If the person is not trained to do the task of his previous workstation or the next workstation, then it may not be possible for him to perform the task at different production rates. So, in most of the assembly area, if this is the workstation assigned to a worker, one, he should be able to do the work of the previous two workstations and he should be able to do the work of next two workstations also. So, this workstation, this worker 1 is skilled or multi skilled, so that he can do this work of previous two workstation and next two workstation also. That is required for the purpose of change in the production rate. If there is a change in production rate, there is going to be redistribution of work elements, and that will this is required. But for breaking the monotony, he may be given work on a job, or he may be working in the maintenance department, or he may be working in some other department also after some time. So, that can break the monotony. Second important aspect in such kind of a system, balancing a line, flow lines or assembly line, in assembly line is incentive scheme. Now, you cannot there are two types of incentive scheme broadly. One is called individual incentive scheme, and another is called group incentive scheme. Now, in case of a flow line or assembly line, individual incentive scheme is not possible, is not feasible, because the output of the system or the conveyor depends upon the work of all the worker, and one individual cannot influence the output of the line. So, in that context, if we look at this, in flow line and assembly line, we have to go for group incentive scheme, and group incentive scheme has its own disadvantages. Person is not motivated enough, because he find that I am working very hard, but because of somebody else we are not able to earn the enough incentives. So, that is one of the issue with the incentive schemes, because we have to implement the group incentive scheme in flow line and assembly lines, and that may make someone frustrated, that because of inefficiency of the other persons I am not able to earn higher incentives. So, these are some of the human aspects, and another thing which we can take care of these human aspects is we can go for the modular assembly line. we can go for a modular assembly line. That means, the whole assembly is converted into small modules, and then we can have one worker is completing the assembling the complete modules. That will take care of job enlargement also, that will take care of the monotony also. Rather than he is doing the same task 240 times as given in the previous example, he may be doing that modular 20 modules he is assembling in a day. So, less monotony is there. So, that can be we can implement. In the conventional, we have one assembly line with n workstation. In modular, we can have n assembly lines with one workstation. So, that is the extreme case, we cannot have n assembly lines with one worker. We can divide them into in a rational manner, we can have number of workstations, and we can create the modular assembly concept. But in the conventional, there is a smooth material flow and there is no material handling, but quality responsibility cannot be pinpointed. The advantage is the material flow is very smooth, but disadvantage of the conventional system is you cannot pinpoint the quality responsibility, because job is passing through so many workstation, and it is not possible to have the individual incentive scheme. And each worker assemble, but in the modular assembly, if we look at the modular assembly, each worker is assembling the whole job. So, this can take care of the behavioral aspects, quality aspects also, and individual incentive scheme can be implemented. Okay. So, in a conventional system, its material flow is smooth, and but there is a problem of quality responsibility, and individual incentive scheme is not possible. But once we go for the modular, we can follow this, and variability in finishing time doing the job does not affect the output, and we can get the more stable outcome from the line, but the only limitation is suitable for small jobs only. I cannot manufacture the car using the modular assembly concepts. I can assemble small products or components which with the help of modular assembly concepts. So, friends, this was about the assembly line, where we studied the need for line balancing. We studied two types of lines also, fabrication line and the assembly line, and then we studied several techniques how to balance it, and then we also studied the limitations of line balancing, and or the rather limitations of the flow lines in terms of monotony of jobs, in terms of not able to implement the individual incentive schemes. Further, we started talked about certain remedial actions also in the form of job enlargement, in the form of job enrichment, as well as in the form of job rotation also. And we also can use the modular assembly line concept, but that is possible only for the small jobs only. For larger jobs, we cannot implement the modular assembly concept. In the assembly of fan, we can do that, or some other small gadgets, microwave, etc., where we can assemble the sub assemblies, modular assemblies, and then that can be put together in the final product. So, friends, this is about assembly line balancing, various aspects of this. So, friends, this session of small session of 10 minutes is continuation to our discussion on line balancing, where we discussed various techniques, and then we also said that there are certain issues like monotony of the job, incentive scheme, etc., for line balancing. For that, we suggested modular assembly line concept, but modular line assembly concept has its own limitation, that only small jobs can be taken as a modular assembly. We cannot assemble cars or such kind of big products as a modular assembly concepts. Now, friends, let us take one example case study of a assembly system, where the demand of the output is varying. In the previous case, in the case of computers, we said that the production rate requirement is 300 units per day. But in this case, we are finding that our demand is not constant, rather demand is stochastic in nature, demand is uncertain in nature. We are taking 5 demand scenarios here, where scenario A, the average demand is 55 units and standard range is 20. That means the demand is varying from 45 units to 65 units per hour. Similarly, there is second scenario where the mean demand is 55 and range is 30. That means we are taking 40 to 70 units per hour. Third case, we are taking even more variability, that is 55 to with a plus minus 20, total 40, that means 35 to 75. We are taking another where we are changing the mean from 55 to 60 and with a small variation, that is 14, that means 53 to 67, and there is another which is 45 to 75. So, these are some of the demand scenarios we are discussing, we are taking here. We are here studying 4 different policies. One is we are using the constant manpower and production rate. That means, even if the demand is varying or changing, we will continue to assemble at the same production rate, and in the process we are creating inventory and in some cases shortages also. And so, we have to consider the inventory and shortages cost. So, in the second policy, we are not changing the manpower, we are keeping the manpower which is required to produce the maximum production rate, and then we are not keeping the production rate constant, we are keeping the workforce ideal. We are keeping the workforce ideal, we are producing only what is required and keeping the workforce ideal. In the third case, we are changing the number of stations, changing the production rate as per the requirements. So, that is zero inventory policy, no inventory, no shortages. Then the policy 4 is related to maximum manpower utilization policy. That means, we are working with the zero inventory, based on that we decide a certain number of manpower, but manpower is not exactly equal to the production rate. So, we are producing little bit more, so that my manpower is fully utilized, and in the process we built up little bit of the inventory. So, these 4 policies we are discussing for 5 demand scenarios. Let us take one data from a line. It has 60 elements, and you will find element number, element time and immediate preceding elements. So, we are having the data of 60 elements which are required to assemble with the element time and predecessor elements. So, what we did here is we took element number 1, we assemble this line for different production rates, and we found that for 36 to 43 production rate, element number 1 is coming always at workstation number 1. Element 2 is also coming at workstation number 1, up to element 9 they are coming at workstation number 1 for a low production rate, that is 36 to 43. Then element 12 and 13 are also coming at workstation number 1. On the other hand, there are elements which are coming on workstation number 2. Like this. If we compare here, if we are increasing the production to 68 to 75, then we are finding the production rate is high. So, less time is available to the worker. So, he is able to perform only 5 elements, element 1 to 6 on workstation 1, and then this element on the workstation number 1. He is able to perform element 1 to 5 and element number 9 on workstation number 1. So, like this. So, what we are finding is, as the production rate increases, cycle time decreases. So, less numbers, less elements are allocated to a particular workstation. So, in this manner we have done the exercise for different production rates, and we determine the location of the different elements. For all 60 elements, we have worked out that on which station they are going to be processed. You can see that if the production rate is high, only 5 workstations are required, or if the production rate is high, 9 workstations are required. Then from this information, we calculate that whether element number 1 need to be trained by some other persons or not. How much additional person need to be trained for this, for different demand scenarios. Element number 1 always coming on a workstation number 1. So, no additional training is required, but this element number 7, sometimes it is coming on workstation number 1, sometimes coming on a workstation number 2. So, training of person, one element is required. So, like this element number 11 always coming on for this particular production rate is coming on workstation number 2, not required, but in some cases it is coming on 3 also. So, additional training is required. So, in that case, in that way we have determined what is the training needs of these elements, how many more persons or workstation need to be trained for different elements, and this way we have calculated the need of the training, and based on that we can calculate what is the total training need. So, 55 elements, man elements need to be trained for a lower production rate, 112 need to be done for this particular category of demand scenario, and 88 need to be trained for this 5th level of demand scenario. So, in that way we determine the requirement of training. Now, we are drawing the Venn diagram to find out what is the additional training. As one example, if my production rate is varying from 60 plus minus 7, that is 53 to 67, then which are the elements which need to be trained. We found that this set A is for a production rate of 53 to 60, and set B is for 61 to 67. So, we are finding that for a production rate of 53 to 60, element 1 to 8 are coming on workstation number 1, but if we increase the production rate 1 to 6 and 22 element is coming on workstation number 1. So, in that way we have determined which are the elements which will come on workstation number 2 for production rate of 53 to 61, that is set A, and 61 to 67, that is set B. So, in that way we calculated, we determined with the help of Venn diagram how the element in the common, they will always remain at workstation number 1. So, there is no change in their location for both the sets A and B, that is the common area, union area of set A and set B. So, in that way we are finding that for if we have to operate within a production range of 53 to 67, 26 work element need to be given additional multi-skill training. Now, so in that manner, for different demand scenarios we have determined the additional training requirements. For demand scenario A, 55 elements, worker element need to be trained. For scenario B, 112, scenario C, 112, scenario D, 26, and scenario D, E, 88 element need to be there. Also, as I said, for a low demand rate 5 workstations are sufficient. For a higher production rate we need 9 workstations to perform the task. Now, friends, coming here we are taking two extreme situations. One is a production rate of 43 units per hour, another is 75 units per hour, and we found that how the elements are getting distributed. 5 workstations are required for 43 units per hour and 9 workstations are required for 75 units per hour. So, you can see that how the distribution of elements, these 60 elements keep on changing with respect to the production rates requirement. Now, let us see the cost analysis of this, because ultimately the it is the cost which will dictate whether our options are good, whether our decisions are good or not. So, here we are taking 5 relevant costs related to this decision. One is the inventory carrying cost. Depending upon the policy which you are using, whether you are using a constant production rate policy or you are using the change policy by changing the manpower, there may be a shortage cost. Then there can be manpower cost, because number of workers deployed will affect that. Then there will be changeover cost also. If we are producing at a constant production rate, there will not be any changeover cost, but if you keep on changing the production rate as per the demand, then there will be a changeover cost also. And fifth is the additional training cost. In case of constant production rate and constant manpower, there is no training cost, but if you are changing the production rate, elements are getting shifted from workstation to workstation. So, additional training, multi-skilling is required. These are some of the parameters we have taken, we have assumed in this case. We said that average demand is 55 units per hour, range of demand is plus 20 units, that means 45 to 65. Nature of distribution, we have taken uniform, we can take normal distribution also, some other distribution also. Product cost, we have taken rupees 500 per unit. Inventory carrying cost, 20% of that, around 100 rupees per unit per year. Shortage cost is 1000 rupees per unit per cost. Changeover cost is rupees 100, and worker wages are rupees 400 per month per worker, and training cost is rupees 3000 per worker element. So, based on this, we have done this analysis for different 4 policies. Policy 1, constant manpower and production rate, constant policy 2 of constant workforce, policy 3 of zero inventory, and policy 4 for maximum manpower utilization policy. So, we found that in case of constant manpower, there is no additional training requirement. So, number is 0 here. Whereas, in policy 3 and 4, where we are changing the manpower, so 55 element need to be trained, and 55 we have multiplied this by the previous slides. We are having what is the training cost, 300 rupees, 3000 rupees per person per element. So, 55 divided by 3000, the numbers are coming here. Second, inventory cost. In this case, there is no inventory, but in this case we are having inventory of 63.92 or 4.34 and 2.36, and by taking a rate of 100 rupees per unit per year. So, this is my inventory carrying cost. And in the same manner, there are shortages. In this case, shortages are not allowed. So, like this, and then we are presuming that we are getting a service level of 96.39, 93.8, and in this case we are having the, because there is no shortage in this case. So, we are having a service level of 100%. Similarly, average number of changeover, there is no changeover involved here, but some changeovers are involved here. So, there is a changeover cost also corresponding to this. Similarly, number of workers required, 7 worker constant rate is required. In this case we need 6.8, and in this case we need 6.34. Maximum number is also given, and based on that we calculate, and we find the total relevant cost of the 4 different policies, and based on that we can say that policy 4 is the best policy. Policy 4, where you change the production by changing the production rate, but produce if not exactly the requirement, but equal to the manpower deployed, whatsoever that in this case you say that this is my demand. Based on demand, identify the number of persons required, number of workstations required, then operate the workstation not as per the demand, but as per the maximum production possible, maximum production possible. So, in the process maximum production possible, and in the process we are creating some inventory, and that inventory we are taking care when we are going for the next period. There we say that demand minus inventory available, and based on that we calculate number of workstations, and that is where you will find there is slightly less number of workstations are required in policy 4 as compared to policy 3, because we are producing not just equal to the demand, but equal to the maximum capacity of the workstations. So, this is friends a case where we have seen that if the demand is varying, how we can make our line balancing dynamic by creating a multi-skilled manpower and dynamically balancing the line. I hope you have enjoyed this unit of line balancing. It is very important unit, very useful unit, and you will find at several places the applications of this unit in the service sectors also, as well as in manufacturing sector. Wherever there is a flow line and number of workstations are working to provide a certain service, we have to balance the line, and there may be some human factors and psychological factors, as well as uncertainty factor will crop in, and then we have to address the situation in a scientific manner and in a artistic manner. Thank you very much for, thank you.